Okay, well, thank you. So welcome everyone to this Julia presentation, a bit general Julia things. So this will be about workflow tips and also some stuff that's new in 1.9, which I think is some quite exciting stuff. I have a link to the slides here, and I also have a repository with the files I will show. I was supposed to paste this in the chat, but I forgot, but I will have them later as well, and I'll paste it in the chat later. If you want, maybe you can take a screenshot or something, but they'll be up later. So just very short introduction about me. I work at the Julia Hub, which was previously known as Julia Computing. I used to be a PhD student at Chalmers and doing materials and computational mechanics. But unfortunately, or fortunately, depending on how you look at it, I did not finish that. I started programming in Julia, and that sort of took over. And then I started at Julia Computing after around 3 years of being a PhD student. Right now, I work a lot on the different open source projects and tools, and also on the Julia releases. So some examples, the package manager, the debugger, package compiler, and then I put version 1.9 here in exclamation mark because that's been a release that's been worked on for a long time now, and it feels that it's getting pretty close right now. So I'm excited about that. So a little bit of an outline of this presentation then. I'll talk a little bit about workflow tips, and this is just general tips and tools and packages that I think improve on the workflow, and based on, I think I started Julia around 8 years ago, so it's sort of my cumulative experience based on that. And then I'll move on to 1.9 then and show some highlights from there. Specifically, I want to highlight the caching of native code, package extensions. You can do something called heap snapshot, and then what I call the first free standard library has been introduced here, and I will detail what I mean with that later when we get to that section. But first, let's start. So most of you are maybe not surprised to see Revise here as the first slide. I would say that's the most important workflow tip. It was maybe so important that maybe all of you already know about it, so I figured maybe I shouldn't even put this up, but yeah, since it's so important, it felt incomplete to not have it in here. And what it do is that it allows hot reloading of code, so you get a very fast debug cycle. You don't need to restart Julia, you can just change your code and your function is immediately updated. And I wanted to show a little bit of demo here instead of just showing slide stuff, so I'll go to my VS Code window, and I hope that the text size is big enough for you to see there. So here I have a little toy package. I call it my package here, and it has a function here called greet, and it just prints hello world. So I'm going to load Revise first, and then I'm going to load my package like this, and then I can of course call this greet function. And if you can see here, it printed out hello world here. But maybe now I go and change it to hello Norway, for example, and now when I run this function, it's immediately updated here. And without Revise, you would kind of have to restart Julia and reload the package to get this updated function. But let's include Sweden here, so no one is left out. Hello Sweden. So with Revise, you can do these very fast changes in your source code, run the function, look at what the changes is, and so on and so on. So if you have a bug or something, you can add some print statements and some show stuff. And yeah, I think this is a very big performance improvement over having to like restart Julia, load the package again, and then call the function. And one little bit of a drawback with Revise, or one thing that it cannot do very well yet, is to revise types. So if you have a struct which has some fields in it, and then you change the type of one of those fields, Revise is going to complain. There's been some attempts here to work around this with some other things, but I tried this earlier today and it didn't work very well. So I would say it's still a bit of an open problem. For most of these workflow tips, I also have a list of references then. So if you look at the slides later and you're more interested in, for example, Revise, then there's also some references to presentations or blog posts and so on. I'm not going to go into these now, it would take too much time, but they're there for sort of a later, if you want to look at the slides later. The second one I have is called OhMyREPL, which maybe also is quite known, but it provides syntax highlighting and some other goodies in the REPL. It something called bracket matching. So if you write an open bracket, it automatically writes a closed one. You can sort of set something like that called the output prompt. I will show that. You can do some fuzzy REPL search and so on. And to install it, you just load the package, and you can do that at the startup if you have it in your startup file. And on 1.9, it starts up pretty fast. Before, on earlier versions, if you loaded OhMyREPL and you started typing, it took like a half a second before your first letters appeared. But on 1.9, with the new stuff, it's pretty fast. So if I go back here, and as you can see, I already have some syntax highlighting here in the REPL, and that's because I have OhMyREPL loaded in the startup file. So you can see here it colors keywords in different colors, and it has color function calls and so on. And if you want, I think this is how you do it. It has a bunch of color schemes, and you can choose a different one. Let's say we want to have this one. I think you do like this. And now we have, if I do function, it's slightly different colors now. So depending on what you like, you can choose different color schemes. And many of these have been contributed by the community. Let's see, there was some other things I wanted to show in OhMyREPL. It was string errors. Yeah. So the REPL search, if I do Control R, which is the default REPL search, instead now it gives you a fuzzy search view. So if I write revise, for example, it shows some stuff that are not exactly revised, and then you can go up and down here. So I think this is a little bit better than the default Control R behavior. It can also, if you write something that will error with the syntax error, so if I write 2E500, actually let me go back to the default color schemes, it shows better there. So if I write something like this, 1E50,000, this is a very large number, and Julia will actually error when you execute it. So this syntax highlighting knows when you write something that is that will likely error, or will error for sure. Like this is not a character literal, and it will color it in red. And if you write a string, you can see it has some highlighting for the string, but if you do interpolation, for example, something like that, it knows that the string part is only the second part, so this one is yellow, but the interpolation here is actually Julia code, so that's highlighted as normal Julia code. Then there was output prompt, so you can use the function set output prompt, and you can say what color it should be and what little token here and what it actually does. It's best to show with an example. So when I ran it now, when I ran 1 + 1, it has a little thing here that shows 2 because 2 got returned. But if I print something, it doesn't show this thing because this was just a print statement. It didn't get returned, but if it would be actually return the string, it would show this here. So you can look at the documentation for it, and you can play around a bit, and being able to see these errors and having a bit of syntax highlighting, I think can be pretty nice. Oh yeah, and the bracket thing is that if you type a bunch of opening brackets, it matches these close brackets, and if you take them away, it also takes away. And if you have too many close, for example, it shows them in red because you have too many. And yeah, it works for different types of brackets. So the next one I talk a little bit about is a package with the nice name of Cthulhu.jl, and many of you have probably tried the @code warn type or @code LVM, @code native, and so on. And it has similar functionality to that, but I wrote it's on steroids here. It's way more powerful. So for example, you can interactively step into function calls. You know, when you do code warn type, you have to say what function you want to look at the one. But if the function is kind of deeply nested, then that can be a bit annoying to sort of get to that function. But with Cthulhu, you can step into things a bit more like you would do with the debugger. And then you can look at generated source code, the lowered code, the LLVM, the native code, and so on, and show type instabilities. And one pretty new feature is that before you could only see, for example, the types on the lowered code, which is sort of a version of the code which Julia has processed and done it more simple for itself, but it might be a bit harder for a human to read it. But with this new feature, you actually get the types annotations on the actual source code that you would write it. And I'll show that now. So I have this Cthulhu file. So first I just want to show very basic usage of it. I I load Cthulhu, then I have a very simple simd sum here that just loops and accumulates something and returns it, so it's just a sum. And then I use this @descend macro, which is the Cthulhu way of like, okay, I want to analyze this call. So now I descended into this, and we can see here now that we have the types here annotated on the actual source code itself. So it sees that there's the function simdsum v, so it looks exactly like here, except now we have the types annotated. And we can also step into different functions here. I'm not going to do that now, but we can see now that we have the source code here, but we can also look at the typed code, which was the default before. So this is simpler from the point of view of Julia compiler's version of the code, but from a human it might not be so simple. We can look at the LLVM code, and it's possible to enable syntax highlighting. So I'm pressing various shortcut keys here. That's let's see, syntax highlighting. Okay, now so this is the LLVM code, and you can see here it does some SIMD stuff, and we can look at the native code with this shortcut. And yeah, I'm on a Mac M1, so this is ARM assembly code that I don't know very well, but this looks like it's doing some SIMD stuff. So that was sort of basic usage of replacing the add code, warn type, and so on with Cthulhu. Then I want to show another thing very quickly. So here I have a function that's test sort. It just does something n number of times. We have a list here, and we push to the list a random number, and then we sort it. And then we can, for fun, we can time this, doing it 10 times. And we can see here that we allocated 1 million allocations for this, and it took 0.3 seconds. So now we might wonder, why did we allocate so much, and why is this kind of slow? So if we start descending into this thing again, so we can see here the source code, and we can see that it has annotated the types here. And one thing we can see is that the list here is a vector of any. And if you're a bit experienced with Julia, you will know that if you have a vector of any here, it can be, things can be slow. So if I'm just gonna dig into this. I'm just gonna jump into functions here until we get to something interesting. So this is sort of the power of Cthulhu, that you can jump into a big function like this. And now I'm a couple of functions deep in, and I can look at the source code here. Now we're in the sort function in base, and we can see here that we have a bunch of any's, and these are colored red because they are not concretely inferred. And this is what makes the code likely slow. So if we want to fix that, we can make this into a float 64 here, and that should, if I now, oh, I exited Julia by accident here. But if I do this and then I run it again, you can see now we have only 140 allocations, and it was 15 times faster or something. So it's just a way to use Cthulhu to sort of dig down in your code and see type instabilities and things like that. So far, many of these things might have already been known, but I want to talk about something that's a little bit maybe unknown, and it's because it's not very well documented. But there's a thing called the REPL AST transforms. And what you can do is you can insert a little function that transforms the AST, or what the input to the REPL, before you actually evaluate it. And there's actually some cool stuff you can do with that. But as it says here in the link I did, it's kind of not very well documented right now, so that should be done at some point. But I wanted to show you anyway. So with this code here, you can push something into the current AST transform, and a function that modifies the expression. And the function I use here is called twice. And what that does is that it takes the expression and it does it 2 times. So if I do this piece of code here and I write something in the REPL, like hello Norway, it prints it twice, and then it returns nothing comma nothing, because that's what this evaluates to. So this was just a very simple thing to see how this could be used, but this is not very useful. So what are what are cases where it could be useful? Well, if we get a bit more creative, we can look at doing some side effects based on the input AST. So for example, you could look at AST and see if you have some macro calls in there and automatically load the packages that those macro calls use. So I have a friend called Fredrik Ekre, and he has a repository here with his dot files. And in his startup file, he has a pretty big expression here. And what he does is that he looks through the expression and see, does it include at B time or at benchmark? Then you probably want to load benchmark tools. And then it does that automatically. So I'll show you how that works in practice. So here, let's just start Julia from scratch. If I do benchmark tools now, it's not defined. I haven't loaded benchmark tools, but I can still do B time 1+1, and it says here loading benchmark tools ... and then it ran it. So it's and that's because I have this this code in my startup file. So it saw the at B time there, saw that I hadn't loaded benchmark tools, loaded it for me automatically, and then ran it. Because often if I start with startup file no, you kind of forget that you haven't loaded benchmark tools, and you go, oh okay, fine, load benchmark tools, and then you do it again. But with this one, it sort of figures out what you want to do, and then it loads it automatically. And you can see it has it for benchmark tools, but also Cthulhu, debugger, profile, and so on. And you can add your own favorite things here for common packages, and then you don't have to think about loading them. You just do the macro, or it could also be functions here or anything, and then it's going to load those packages automatically. And I wrote a little homework here is to try and come up with other cool applications that you can use these AST transforms for. What would you... If you get in some input, what could you automatically do? Like you could load the packages here, or I also show he has added some key bindings. So if I do just :Q, it exits Julia. If I do :R, it restarts Julia, and so on. It's similar to some Vim keybinds there. And so you can do quite a lot with these AST transforms. Looking at the time now, so yeah, I think I have time for this. So TestEnv is another pretty nice package, and it allows you to activate an environment that includes the test dependencies of that package. And you can argue that this is sort of a missing feature of the package manager itself, and it should probably be added there at some point. But for now, you have to use this external package, and when you have the environment with the test dependencies, you can interact with the test code more interactively, like you would with a normal file. So to give an example here, I have my package here, and if we look at the project file, it has some extra stuff here, and these are the test-specific dependencies. And when I run the test, if we look at my package, I have this very simple, that takes a derivative of a polynomial, and then in the test, we call this function, and then as some verification, we verify it against forward diff. Oops, that does automatic differentiation. Of course, you wouldn't do it in real life like this, but just as an example. So the problem now is if I go start my project and I just include my run test file, it's going to error because forward diff is a test dependency, so you can't load it here. But if I do load a TestEnv package and then I do TestEnv.activate, now I'm getting put into this temporary environment. But in here I have forward diff and I have test. And now I can just include this run test file, and it passed, and maybe I want to step into this in the debugger or something. So you basically get a new environment with the test dependencies active, and you can play around with this like it would be a normal code. Then another one is something called live server and Revise for documentation. And what live server does is that it watches and rebuilds documentation for you. So you can start live server and it's going to check for any changes, and then it rebuilds the documentation. And we also use Revise to update doc strings. And I gave an example here in of some code that uses this. This is in Ferrite, which is a finite element toolbox that we used exactly this live server thing in this little convenient script here. But again, I will show it live demo. So in my package here, I have some documentation. It's just very simple. It's just an example package, and then it put the doc strings of the packages there. Then I have this live server script, which just does very simple. It just activates and instantiates it to make sure that, and it calls live server serve docs with the documentation folder and the source folder and so on. And then I have my make.jl, and what I do there is I look if I'm running the live server, and then I enable Revise to do the revision here to update the doc strings. I think it's better to show how it works in practice. So if I do Julia project here and I do live server, now it's going to run my live server script, and it builds the documentation, and then it starts a server for me here at localhost 8000. So here's this little package source code then, the package documentation. Now if I go into, for example, index here, and I go with hello Norway, as I did before, and now when I save it, it reran the documentation script, and it has appeared here. And the fact that I used Revise is so that I can go into my package here, and now I do hello Sweden here in a doc string, save it. Now I'm not sure why. Before it showed hello Sweden here, and that's what it's supposed to do. I'm just going to test the other function, see if there's something weird here. But for some reason, the doc strings don't work to update now. The point of using Revise is that they should update. I'm not sure why they don't. They did earlier today, but I'll figure out why that happens at some other time. But it should work like this, and we're using this for Ferrite this, and it works there. So I don't know exactly what happened there. In 1.9, you can also change the REPL's active module. So most of you probably know that when you start a REPL, it has the main module as the active module, and that's sort of where the expressions are evaluated. But this can now be changed with, if you write the name of the module and you press the meta key and then M, you can change this active module. And the meta key is most often Alt on Linux or Windows, but it can also be, for example, the escape key on a Mac. There's an example. If I load my package here, and then I'm going to type the next line here, I'm going to write my package and then meta M. So I do that, and then the prompt changes a little bit. It shows my package here in these parentheses, and if I type this little macro thing here that shows what module am I currently in, it says, oh, you're in the my package module, and then I can just call the greet function in there because I'm in that module. I don't have to prefix it with my package. And here I'm switching. You don't see that yet, but I wrote base math and I pressed meta M, and now I'm in the base math module, and I set a variable there. And now when I look at that variable from main again, it sets to 10. So you can sort of jump around between different modules to have them active. And if you're, for example, developing a package, it's pretty convenient to have that package as the active module, because then you have access to all the symbols in there. You don't have to like prefix with the module name and so on. So there are many other useful tools, but in the interest of time, I can't go into them very deeply. So again, I just put a list here of useful links and so on, and some of them have had presentations at JuliaCon. So this is sort of, if you look through the slides later, you can look at these, but because I think these are also useful, but they didn't make the cut this time to actually end up in the presentation. So that was it for the workflow and the tool section. So now I'm excited to talk a little bit about what's new in version 1.9. Hopefully out in, I don't know, it's scary to say some dates, but I would say maybe 2 weeks or something, if everything goes well. So the first and most important thing I would say is the caching of native code. So before 1.9, native code was not cached, and native code is sort of what ends up actually running on the processor. And in Julia, that's the job of LLVM to generate this. And generating the native code could be a big bottleneck in latency. Like this is not an easy task that LLVM is doing to generate all this native code. So if we look at some timing for 1.8, first we timed loading plots, which took around 3 seconds, and then the time to actually display a plot object took around 3 seconds. Now, if we look at 1.9, actually the time of loading plots is significantly better, and that's not due to this. That's due to other improvements. So thank you for that, but that's not the point here. The point is to show how that this time to plot has gone down from 3 seconds to now it's 0.3 seconds. So that's a big improvement, and to me this is a very exciting time, because the complaint about Julia so long has been for these time to first plot, as we call it, and now there is a chance that we could start working on actually getting this to be pretty well. We have an upcoming highlight for 1.9, which is of course not out yet, but I took an image from that, or a figure that shows the impact on a lot of different packages when caching this native code. So what it plots here is the TTL, which is the time to load, TTFX, which is time to first doing something like plotting in case of a plotting package, but it might be solving a differential equation if you're doing a differential equation package or something. Then it also shows the cache files in megabyte. So the first thing we can see is that the time to load is actually lower in general on 1.9 than it was on the other versions. I'm not sure exactly what happened on 1.8, but the load time there seems to be pretty bad. But on 1.9, it's still even better than 1.7. So that's just the load time. But then the important part is the time to first X here, where there's been big improvements. Both 1.8 made a pretty big improvement in general, but 1.9, a lot of these things, maybe there should be a log scale or something here, or basically on the very, very small here. And you can see these packages are pretty popular. It's CSV, data frames, Revise, differential equations, and same image stuff. So they are now much, much faster at getting their job done. Now, a little bit the drawback then is if we look at this cache file size, like how much is actually stored on disk for these things, we can see ordinary differential equation is way high. I think they do that they precompile things for very, very many different solvers, and it goes a little bit bananas. But for most other packages, it has increased, but it's still within, like, let's say 50 megabyte or under here. And I think most people are pretty happy to accept a little bit more storage for faster time to first, whatever they want to do. So this is the big one, I would say, for 1.9. Then the second one, which is pretty interesting, it's something called package extensions. And I just want to paint up a little bit scenario here for talking about when it's useful. So let's say you're writing a plotting package and you want to support plotting a lot of types in the Julia ecosystem. You want to be able to plot data frames, some units from Unitful. You want to be able to plot contour plots and different colors and so on. There's probably a big list of packages here that you want to support plotting. And typically what you would do is you would just extend plot on data frame, and you would extend plot on some Unitful thing and so on. And the way you get access to this data frame type is by just loading the package, and then you can write this extension. But adding dependencies has a bit of a cost. Firstly, users of your package has to install all these packages then, all the dependencies. It's usually not so bad to just install packages, but if you do something like CUDA, which is like GPU computing, it has to download quite a big runtime to do it. So in those cases, it can be a bit annoying. If you're not going to do GPU computing and you still have to download this whole CUDA thing, it can be a bit annoying. But the big time is the load time cost, which I would say is the most significant. Just loading all of these packages all the time, when it's quite unlikely that the user maybe is even going to use any of these functions. Like maybe the user just want to plot some lines and so on. You still have to pay for the fact that you're loading data frames and so on. So it feels a bit bad to add all these plot functions then, because you're kind of loading your package, but unconditionally loading all of these things. So the package extension, then you can think about it is that you create a little mini package, and that gets automatically loaded when some other packages are loaded. And for those of you who have used requires, it's similar to that. That also worked the way by it evaluates some code automatically when a set of packages are loaded. But this is sort of a bit more first class, so it supports the pre-compilation of the conditional code. You can add compat constraint on these optional dependencies. It's better for what we call relocatability, which is in package compiler when you create something on your own machine and you want to distribute it to other machines. These package extensions support that better. And what typically an extension does is that extends some method in the parent package to types in another package. So if you have a plotting package, you can extend your plot function on a method in, let's say, data frames. And you will only pay for that code if someone actually loads data frames. And here's a link to the official documentation, but maybe more interesting is to see some usage of package extensions in the wild, because people have already started using this on the pre-release of 1.9. So one example is for forward diff, which is an automatic differentiation library. On 1.8, it loaded static arrays unconditionally because it had some code that it extended for static arrays. And it took around 0.6 seconds to load forward diff. But in 1.9, the static arrays is an extension. So if you just do using forward diff, it doesn't have to load static arrays. So you can see here that the load time is significantly better. And you're only paying for this static array thing if you actually end up loading static arrays yourself or some other package end up loading it. So it's a little bit of a thinking here that you shouldn't pay for what you don't use. And as another example, it happened to be another AD package, which is called Zygote here. And here I'm loading tracker colors and distances because those are the things that in Zygote used to be done with requires, that if these were loaded, requires was used to load some supporting code. And before, without extension, using Zygote after these were loaded took 0.9 seconds because it loaded Zygote, but it also loaded this bonus requires code for these three packages. And was not precompilable, for example, so it had to basically load that from scratch. But now with extension, if you load these three packages and then you load Zygote, it went from 0.9 seconds to 0.3 seconds because these extensions can be precompiled and they're much faster to load that way than the way requires did it. Moving on, another thing that can be pretty interesting. Sometimes you can feel like, where did my RAM go? What's taking so much memory? And in 1.9, there's a tool called a heap snapshot, which sort of takes a snapshot of all the memory in the Julia session and dumps it to a file. And then you can actually use Chrome DevTools to load that file and look at all the memory. And the reason why Chrome DevTools is used is because that just happened to be the one it has a pretty good user interface for that. So as an example here, I just created a vector of random elements, 10 million here, and then just a bunch of random strings. Now these are in the Julia session, like they're in memory. Then I can load profile and I can take a heap snapshot of this. And it's going to take a second or two and it's going to dump to this file. And if I go to Chrome now and I go to the debugger or the tool in Chrome, and then I can load this file that Julia dumped. And I've loaded it here. And then here you can see all the memory that Julia uses. So it's a bit fun. Here you can see the REPL history provider, which is the thing that provides you with the history in the REPL when you press arrows and so on. And if you go into that, you can see the history here. There's an array of strings. And then here are a bunch of stuff that I have run into the REPL, which got, that's part of what Julia had to load. So it's in the memory there. And you can search on things. So I think I called the variable strs. So there it is. And we can look into it and we see we have these, it's an array of string there. And we can see the first one was NGO, the second one was 99. And if I look at my slide again, the first one was NGO and the second one was 99 and so on. So if you say your session is using 10 GB of memory and you have no idea why, you can now just dump it to a file and then investigate what's going on. Finally, I want to talk about the first, what I call free standard library, and that is delimited files. And that was a very small standard library, which very few people used, which is kind of intentional because this is sort of a little trial thing. And it still comes bundled with Julia. So if you just download Julia, you can still load the delimited files just like normally. But the important part is that it can be upgraded independently of Julia. So it kind of acts like a normal package as well. And that's pretty great because it means that you can get much faster bug fixes for it. Like you can just make a new release of the package. It means that bug fixes get propagated to older Julia versions. Let's say there was a problem with delimited files and we fixed the bug there. You would only get that to the next Julia version, or at least until the next Julia patch release where it might have been backported. But with this, you would just release the bug fix and you would just update your packages and it would be there. It means it's easier development for contributors to standard libraries in the sense that it works just like a normal package. It's also not in the what's called the system image, which is loaded when you load Julia, and all these standard libraries that are in the system image puts somewhat of a cost in, for example, the start time of Julia, because even if you're not using the delimited files, the fact that it's in the system image means that it's a cost when you load Julia. And if this experiment turns out well, we might try to do that with other standard libraries to also sort of free them, because there's not that many drawbacks to it. One drawback is that packages that are in the sys image tend to load faster, but load time has gotten pretty good. And if the load time regression is significant, then maybe we're not going to do it until it's fixed. But yeah, I would suspect that it's going to be a little bit similar of this for other standard libraries because there's so much advantages to it. So just as an example here I have a fresh Julia session. I'm just loading the delimited files. And then if I look at the path of this module, like where did it get loaded from? It shows this long path there. That's because I'm using Julia up here, but it's like inside Julia, it came bundled with Julia. So this is the path where it got loaded. But if I'm typing add delimited files in the package manager, it's gonna install a version of it here. And if I'm loading it and I'm looking at the path again, it shows me it's in the normal packages folder in .julia. So here it's using a version 1. And if there would be a new release of the delimited files like 1.9.2, if I would just update my packages, it would use the updated one. So yeah, that's I think that's it for the sort of free standard libraries. And yeah, with that, I think I'm done. I want to say leave a little bit of time if there are any eventual questions. I want to say thank you. I put up the slides here in a short link. I'll paste it in the chat later too. And then the actual files, the examples I used here with my package with the documentation and you know, everything here is inside a repository. It's on my GitHub on my latest repository, which is DigiWell Seminaria Julia here. So yeah, with that I want to say thanks.